Hey, starting chapter 11, circles. So section 1, we're looking at lines that intersect circles. So all the different ways that could happen. So we have a lot of different situations to look at in this section. So this photograph taken 216 miles above the surface of Earth. So pretty high up, but still you can see only a small piece of the Earth. So being on the surface, Earth appears flat. As you go higher up, it appears more round. And if you take a cross-section of the Earth, cross-section of a sphere, you have a circle. A circle with center C, we call it really creatively circle C. Or if we're feeling like we want a shorthand, go circle C. Alright? Two kind of spaces of a circle is the interior, that's all the points that are inside the circle, and then also the exterior. That would be any point that is outside the circle. Any point that's on the circle is neither interior nor exterior. It's on the circle. All those points are equidistant from the center of the circle. That equidistance, all the way around, call that the radius, okay? Now, different types of line segments that intersect circles. We have a chord. That is a segment whose endpoints are on the circle. We also have what's called a secant. That is a line that goes through the circle at 2 points. The secant goes through it, extend infinitely in both directions, but take those ends off, break them off, left with just the segment inside the circle, you have the chord. So every secant has a chord. A tangent is a line that's in the same plane as the circle. So they're coplanar, they kind of lay flat with each other, but they only intersect at exactly one point. The point where a tangent line intersects with a circle is called a point of tangency. Again, very creative. Tangent line where it intersects is the point of tangency. So we're kind of identifying these different types of lines and line segments. A chord is the line segment. So we see JM, a line segment with the endpoints on the circle. A secant would then be JM also, but now it's a line. Okay? And for chords, I think I forgot km. Km is the diameter, but a diameter is the line segment, both endpoints on the circle, so include that as well. A tangent would be line M. A diameter, so a diameter, already addressed that. Diameter, so a diameter is a secant that goes through the center, point L. So km is that also. Radii, we have 3. JL, KL, boy that looks sad. KL, there we go. And ML. You'll notice all those radii have point L as a point M because radii go from the center to a circle. Pairs of circles. So now looking at two circles existing together. two circles are congruent if and only if. So a biconditional. This goes both ways. If and only if they have congruent radii. So if circles are congruent, then the radii are congruent. If the radii are congruent, then the circles are congruent. So it goes both ways, okay? Concentric circles have the same center and they're coplanar. Two coplanar circles that only intersect in one point are called tangent circles. So they could be internally tangent or externally tangent. So in this graph, identify the length of each radius and also find the point of tangency. So radius circular, I already have there, is 2. Radius of circle S, I already have there, 1.5, just count how far it is. But the point of tangency, where they intersect, right there. So we'll say the point of tangency is a -2, 0. A common tangent, kind of common sense here, is a line that's tangent to both circles. So it has in common between two circles that is tangent. That's the common property of this line with both circles. That can happen when both L and M are external. Can also happen when they're internal tangent lines. They kind of X go through each other. We also have tangent lines. A tangent line, if a tangent line to a circle, then that tangent line is perpendicular to the radius. So no matter where that tangent line is, so it's going to be perpendicular to a radius. You can just do it over here. And if you draw a radius out to it, they're going to be perpendicular. And then the converse, if a line is perpendicular to a tangent, so you already have that property of perpendicularity. That's a word? I don't know. If the lines are already perpendicular, one's a radius, you know the other is a tangent line. Early in its flight, the Apollo 11 spacecraft, the first one that took men to the moon, orbited Earth at an altitude of 120 miles. So what was the distance from Earth horizon to the spacecraft? So how much or how far on Earth could they see? So if we get the picture, and we draw a spacecraft, and I'm a really good artist, you're going to see here. There we go. That's a good spacecraft. Looks like I'm bombing Earth. Oh boy. And then let's draw something. So the center, the radius of the Earth, about 3,900 and what? 59. Okay. And then the spacecraft, not to scale, was 120 miles above. So then the question, how far from the spacecraft to Earth horizon? Maybe I could do it better. Start here. So how far is that dashed blue line? Well, that dashed blue line is a tangent line. So we draw another radius out to have a rectangle. This is also 3,959 miles. So then you could use some Pythagorean theorem to find the dashed blue line. Example 4 looks at another theorem. Two segments are tangents to a circle from the same point. So from point A, then the tangent to circle B, then the tangents are congruent. So take a look at other examples I didn't finish. Check your work with my completed notes online.